can hear you well, at least I can.
Okay, so it seems that now it's working, because
Yeah.
for a couple of seconds it appears an error message saying that something is wrong, but now it seems that it's working. So thank you, and hi everybody, by the way.
Hi, Carlos. Thanks for joining. Yeah, I had the same message here. I still have it, but seems to work nevertheless.
It's Red here.
Hi, Red. Welcome.
Thank you. That's good.
Okay, let's maybe wait for 2 more minutes. I think people are trying to create their Decker accounts.
Okay, so I got a CodeMD page, but I don't see where I had a pane to enter notes, but now I don't. I killed it somehow.
You okay?
Sorry.
So can you just click on the link again and open it again? Or?
Well, the link that you pasted in takes me to the ICNRG page, and then when I click on the CodeMD link there, I see notes, chairs, presentations, Zeno.
So you are actually no.
Okay,
you're at the right page. So you are looking at the say
right. So
presentation view.
I see now the Blackboard with the agenda and everything, but when I try to edit it, okay, now I can edit. All right.
Okay.
I went through the authentication step. Now I can edit.
Okay, great. Yeah, I think everything is a bit rusted, so, but I think we'll manage. Okay, shall we make a start? So, Dave, are you connected? I can't hear you, I think. Probably muted. Still can't hear you. So at least you had the microphone icon for some time, but now it's gone. So I think you're on mute again. Yeah. But we don't hear you. That could be a local device configuration thing. Still can't hear you. What's going on? So video is fine. Nope.
Okay, so now I see your mic on the participants panel.
But no audio. Audio channel closed error. Okay. That sounds like a WebRTC ICE problem. But strangely, video works, so I'm not really sure what's going on here. Nope. Yeah, it might be a permission problem or a device selection problem.
Better. Is that any better?
Yeah, that's better.
All right, I had to leave the meeting and rejoin.
Okay. Great that it finally worked. Okay, and let's start. Okay, yeah, welcome everybody. Thanks for making it at the end of this week to another ICNRG meeting. Unfortunately, still online, but I think everybody understands why. Yeah, so I'm Dirk Kuscher, and my coach is Dave Oran. And just a second. Before we start, just have to point you to some housekeeping items. So, namely the IRTF Note Well statement. So this basically pertains to IPR. So if you submit anything to our group that has IPR associated, you're expecting to let us know. If you have any question on this, just talk to Dave and me. The IRTF also follows the IETF privacy and code of conduct rules. So first of all, please be aware that so these meetings are typically recorded. And so we also have a privacy policy. Please check that. And so there's also a policy regarding code of conduct and anti-harassment. So in the IETF, but these rules also apply to us here in the IRTF. And yeah, to those of you who are attending ICNRG or IRTF meetings for the first time, so the IRTF is what is called a sister organization of the IETF. So the IETF is setting standards for the global internet. the IRTF, so the Research Task Force, conducts research. So what we are doing here is not standards development. So we may be producing specifications and so on, but and then also publish those as RCs, but this is just to enable experimentation and yeah, just write down specifications that people can use for conducting research. And of course, the hope is that eventually, you know, some insights are generated that may, yeah, guide future standardization work in the IETF. Check out this RSC 7418 for an IRTF primer. Okay, just links to our infrastructure, just for the record. So for this meeting, as usual, all the material is online on the IETF data tracker. Just use this link here. So including these slides. And we typically, we always take notes and produce minutes of our meetings because, well, not everybody makes it, and we have a mailing list where we try to do like the other, or most of the work in the group. And today we are really grateful that Ken Calvert volunteered for taking notes. Thanks, Ken. And so what this typically involves is just trying to capture the gist of the discussion. And so for these online meetings, some discussion you know, takes place in the audio channel and maybe some other discussion in the chat. What we often do is just copy the chat to the notes later as a hint. Okay. Yeah, we are really happy that we have a super interesting agenda today. So we'll just give you a status update after this, and then we have three really cool research presentations. So one by Carlos on Zeno, one by Red and Jaime, I hope that's correctly pronounced, on GT Systems span network architecture, and then one by Junxiao Shi on his thoughts and his work on Nts and an API design for that platform. Okay, so just a quick update on what has happened in ICNRG recently. So we are very happy to report that the group has published 2 new RCs, so round of virtual applause. Thanks to everybody, especially the authors, but also everybody who helped in reviewing this and improving these documents over time. And if you've been around, you probably know that these documents have been developed over quite some time and have seen quite a few iterations. So RC 9138 describes design considerations for name resolution services in ICN. So yeah, what role name resolution could possibly play and what you would have to consider for that. And RC 9139 describes an adaptation of CCNX to low power wireless personal area networks. So this is equivalent to the IETF work in like 6LoWPAN, so IPv6 over these low power PANs. And well, this is actually has quite some potential for you know, enabling further usage of ICN in constrained networks, IoT, and so on. So it's not necessarily restricted to personal area networks, but so this technology could be used in all kinds of networks where that are kind of resource constrained and where you need a really compact representation and so on. So I think this is quite an interesting achievement, and yeah, check out the protocol spec if you want to learn more. Okay, and so in the data tracker, you can also see our various documents, and so these are the active research group drafts, so that we adopted earlier and have been developing over time. So just quickly where we currently are and what we plan to do next. So the other name resolution document is completed and is going to be published soon. So there's one called Nts Architecture Considerations. And we also have a document on doing ICN in LTE, so 4G networks, which is also about to be published fairly soon. So hopefully, I mean, we still haven't.
The one reviewer we're waiting for comments on happens to be the chair of the IETF. So he's been a bit slow in getting his reviews in.
Yes.
So we're hoping that will happen relatively soon, but we're locked on that at the moment.
Exactly. So we have one other specification type document on a technology called CCN Info. So something that like a tool that allows you to collect information about elements on a path in a CCN network. And we last called this document earlier in the year, got some minor comments that were addressed by the authors some weeks ago. And so we think this document is now ready. So there haven't been any technical changes. And so we would, or Dave has just notified Colin that we want to submit this for our IRSG review now. Then we have, say, other important in progress work that we adopted earlier. So, for example, the FLIC specification. So FLIC is like manifest technology for ICN. That we think it's quite relevant, and we would like to get it published, say, early next year. But for that we need more eyes on it. So we need a thorough review by like more people in the group. So please, everybody who has an interest in this, please help in progressing this. We really want to publish it soon.
Let me chime in real quickly. This is a pretty important document because manifests are becoming more widely used throughout the panoply of ICN things. And this it's been implemented, it's had a lot of work done, but the new draft that I submitted about a month ago, it has major sections rewritten. So it really needs a top-to-down review from everybody as opposed to a quick skim. And the quicker we get that done, the quicker we can get it to last call. There's still a few open issues, and those are noted in the document. And we particularly want people to weigh in on the areas where we actually think there are holes that need to get filled technically. Thanks.
Yeah, thanks, Dave. Exactly. And so moreover, we have these two other specifications on traceroute and ping. And so they also have been around for quite some time. And we think, well, actually, technically, they're mostly done. So I think next we would do a last call on the mail list and then ask for final comments.
Yeah, so expect to see a last call on those two documents on the mailing list in the near future.
Right. And then lastly, we have a couple of other documents that still need a bit of work, but could probably also benefit from like feedback from the group. So path steering, if you remember, that is, I think, quite elegant way to make ICN communication stick to some path with a like soft state approach, which is beneficial in many scenarios. Reflexive forwarding was a technology, to have like basically some say soft state in the network that establishes some symmetric forwarding information that we used for the RISE system, for example, the remote method invocation system. So we are still planning some updates on that one, but eventually, so hopefully this can also be finished next year, maybe early next year. Time TLV is a new TLV structure for recording time that we originally wanted to reuse for the LOPAN specification, but then LOPAN got finished say earlier, and so but we still want to publish this as a standalone RC. And so that's like quick summary of where we currently are. And of course, it's also maybe a good time to think about what could be, useful or interesting upcoming work. And so in the area of IoT, so we now have this, say, efficient encoding for LOPAN networks. We earlier talked about, say, ICN LoRa, so low power, long range radio systems. I think that there's quite some potential there. Personally, I'm also quite interested in that. And well, then I think what's really, and yeah, most people know this, what's really interesting in ICN is like new ways to support applications better. And so we will hear from Jun Shao, for example, in a bit about his thoughts. But I think it would be nice to maybe see some convergence or like some good practices, best practices or something in this direction. Then, yeah, we have been talking a bit about distributed computing, also it's in ICNRG, but also in the COIN, Computing in the Network group. And yeah, many of us think that ICN is a really useful enabler for, yeah, also rethinking how computing is done in the network. And so the RISE work or the CFN work that we published earlier are like just two examples, but people may have many other ideas as well. So that could be a general good topic for us. And quality of service. If you remember, we earlier published an RSC 9064 that talked about, say, the potential, so QoS considerations in ICN. And I think was a really nice description of what could be, say, qualitatively much better in ICN compared to IP when you want to do QoS. And so the question is, okay, what follows from that? So do we want to leverage these ideas, maybe specify some mechanisms? There has been some other discussion, other work in ICNRG before. Maybe now is a good time to kind of, maybe take the next step and see what we can do. So these were just Dave's and my thoughts. Of course, this is not a complete list, and by no means we are limited to these topics. So if people have other ideas, just as usual, bring them on, and we will discuss them here. Okay, and so with that, we would start our presentation program. And so the first in our list is Carlos with his presentation on Zeno. And Carlos, I think the best way is if you just shared your desktop or your application window yourself.
Hi, Dirk. So I just enabled the microphone again, and I lost you for a couple of seconds. So
Yeah, we can hear you.
Yeah. So if you could repeat the question, because I really missed it since it was mute for a couple of seconds.
Okay, no problem. Yeah, please start your presentation, and if you could just share it yourself, that would be. I think that's the only way, actually.
Yeah, of course. So let me share the screen. Do you want to share the screen? Yes. No. Okay.
Being
Okay,
started,
so,
and there it is. Except you want to change to, there you go.
Yeah, that's
beautiful.
perfect.
I can enable also my camera so people can just see me. Okay.
Now you have to switch the screen back to window. Yeah, there you go.
Yeah. Okay. Okay. So hi everybody. So first of all, I would like to thank you for the invitation and to say that it is a pleasure to present Zeno here in the ICNRG. So my name is Carlos Guimarães. I'm a senior technologist in Adlink, and I've been contributing to the design and implementation of Zeno, especially focusing on microcontrollers and low-power devices and also low-power networks. So I think there are some shared aspects to what Dirk just mentioned for new works here in the ICNRG. In any case, I have shaped this presentation as an overview of what is Zeno in order to provide a high-level view of its main design choices and its capabilities for those that are not aware of Zeno. But let me start with a bit of context on some of the motivations that led us to design Zeno. And let's first imagine that we have some data, and let's see the journey that it takes since it's produced until it's consumed. So the first thing that happens is that data gets produced by the most variety of entities. They can be robots, satellites, sensors, and so on. And then this data is distributed, and perhaps just inside the same physical nodes, or within the same local area network, or eventually across different geographic locations. And this distribution of data happens because either we want some computations to be applied over this data, or just because we want it to be stored. But then every time some computations are performed over the data, it also generates more data. And typically at this stage, people tend to call it information, but well, it's still data to some extent. And therefore, this cycle repeats over and over again. And finally, we also have the case that we can store data because sooner or later we plan to retrieve it again, just for the fact that we don't store data just because yes. So we can say that in this journey, data goes over a series of alternations between the data being in move, the data being at rest, and the data being in use. And traditionally, there are different communication patterns that are used for each one of these cases. So for data in move, traditionally, we can see push patterns like PubSub being the more predominant ones, while for data at rest, the pull patterns are the most common approach. And what is the catch? The catch is that while data goes on this journey, every time we need to move across data in motion and data in rest, or data in rest to data in motion, we clash against a technology barrier, meaning that these two technologies ecosystems are really fragmented. So on one side, we have the technology to push data, and on the other side, we have the technology to store and to retrieve data. And the problem becomes even worse if we look at the way the current systems are being designed. Just because we are moving away from these monolithic systems where everything runs either locally or in the cloud, and we are witnessing a decentralization and distribution of the different functions that compose these same systems. And the problem is that so the current technologies fail to provide data management that is not only unified, that is location transparent, and also that is simple to put in place and to use. And this is the gap that Zeno is trying to fill in. Okay, so in a nutshell, Zeno tries to unify data in motion, data in use, data at rest, computations by blending together PubSub and distributed queries while providing built-in support for geo-distributed storage and computations. To some extent, we can say that Zeno is a kind of data-centric solution, okay, a data-oriented solution. And it achieves it by not only defining its own network protocol that can operate over different network technologies at different stack layers, but also by providing a set of high-level APIs that facilitates and eases the handling, distributing, and storing of data across a distributed and decentralized system. So if we have here a closer look, a Zeno node is designed by following a layering approach. So on the bottom, we have the Zeno protocol that implements a network layer capable of running above data link, network, and transport layers. Then in the middle, the Zeno defines a set of data transportation primitives that provide support for publish, subscribe, and for query replies communications. And note that here this layer is content agnostic. And then on the top, Zeno defines a set of data-oriented abstractions, which is our API, that allows more complex semantics on top of the real content in order to support, for example, distributed storages, filtering, transcoding of data, and even remote computations. And if you note at this layer, Zeno is already aware of the content and its properties. And then when we deploy several Zeno nodes together, we might come up with a Zeno network overlay, just like the one we have in this slide. And here note that Zeno can either run in the devices where the user application is being executed, but it can also run as a network node. And for that, Zeno defines three different types of entities, different entities. So we have the client, which consists on a user application that is using the Zeno API and that connects to a single Zeno router or Zeno peer in order to communicate with the rest of the system. We have the peers, which also consist on the user application that is using the Zeno API, but here they differ in the fact that they are capable of connecting to multiple Zeno routers, to multiple peers, and also to perform routing and forwarding of other Zeno messages. And then we have the routers, which consists on some software nodes that can route messages between the clients and the peers. And these three roles allow us to implement not only peer-to-peer communications over any type of connected graph topologies, allow us to have brokered communications, and this is especially useful for constrained devices like microcontrollers, because they are not so powerful and they cannot run all the capabilities that are required, for example, to do routing. And we also have routers that are capable of forwarding data to and from other peers and clients. So this is just a quick overview of Zeno, but now let me go a bit under the hood so we can see a bit more on some of the choices we made. So first, how do we address the data? So the way Zeno names data is inspired in ICN protocols like NDN, And it does that by defining a set of byte arrays that are called name segments. And these can be grouped together in what we call a key. And by doing it, we can explicitly declare the interest in some data or in some particular piece of information, or to declare our interest on all data that matches a given regular expression. For example, we have the star operator that is used to replace a single name segment in the key, just like the first example in the bottom. Or we have a double star operator, which is used to replace 0 or more name segments in the key. So in this case, the second example in the bottom. So if we look here into these examples, so one can say that when I have /home/ star /sensor /temperature, I'm getting all the temperature sensors or the values from all the temperature sensors that exist in a home. Okay, no matter what is the room, this key expression will match it. So I can get the temperature for my kitchen, but also the temperature of the living room, and so on and so forth. Then in the second, we are basically reporting or saying to the Zeno system that we want everything that matches a C202 and that is being published in my house. Okay, so this will match anything on any room and any kind of source. And at the same time, then we can also, so it's also possible to fine-grain the selected data at the declaration time by defining some predicates, projections, and a set of properties. Okay. However, I would like to highlight that the key expressions are used to route. So just the part that I showed in the previous slide, but these predicate and projections and properties are only executed in the node that executes the query or publishes the content. And these allow us to filter some data. For example, if we take the second example here, where we have my car dynamics, basically what we are saying is that return me the acceleration every time, so return only the acceleration value every time the speed is above 25 kilometers per hour. And then when we have these keys, when we define these keys for name our data, how and who can make use of them? And for this, Zeno defines a set of entities that can handle keys and values in different ways. So we can have resources, which represents a named data that is represented by a key and by its corresponding value. We can have publishers, which represent a string of values that match a given key expression. So in other words, it represents the entity that produces data. We have subscribers, which represents a sink of values that match a given key expression. So in other words, the entity that consumes data. And we have queryables. And a queryable here represents a well of values for a given key expression. So a queryable is also a producer of data, but the difference is that it needs to be explicitly requested by a query. Okay. And then how can these entities make use of Zeno? So for that, we have a set of operations that are listed here in this slide. So just for me to go very quickly from on them. So we have Scout that basically acts as a discovery mechanism to see who is around, which entities are around. And this is very similar to the Bonjour protocol. We have primitives to establish and to close sessions with the init, open, and close. And it is required to establish a Zeno session prior to any data exchange. The thing here is that a Zeno session is not end-to-end, but is established between adjacent nodes. So between every op, we have a Zeno session. Then we have primitives to declare and undeclare the different kinds of entities. From these declarations, only the declarations for subscribers and queries are actually mandatory. For example, so other declarations for publishers and resources are optional and basically serve to optimize specific mechanisms within Zeno. So for example, we can use a resource declaration in order to map a key or part of the key to an integer. And by doing it, we can save some bytes in the wire every time we need to send data. And lastly, we have primitives to write, to pull, and to query, which basically defines the operations to push, retrieve, and request data respectively. Then one particular thing about the way Zeno implements queries are its consolidation strategies. And although I believe we will not have the time to dig in on these details, let's just consider that we have a distributed database, and therefore several nodes can reply to a given query. In this case, because databases might not be aligned, so the querier might get different replies from the different databases. And to mitigate such cases, Zeno implements a set of consolidation strategies that allows to correlate, combining, and integrating data from different queryables in a single reply. So we have three different types of strategies. None, where all responses are forwarded back to the querier. We have the lazy strategy, where only replies that are more recent than the previous sent are forwarded. And we have the full, where only the most recent replies for each resource are sent back to the querier. And these consolidation strategies are applied in three different stages while delivering the query reply: in the first router, in the last router, and in the reception node. And if we look here at the default values that are applied in these different stages, so lazy, full, these allow us to have eventual consistency by default when using Zeno. Okay. Now going a bit lower in the network stack. So Zeno is transparent from the underlying network topology, and it has been tested over a diversity of protocols at different network stack layers. So we have successfully tested it over UDP, TCP, TLS, QUIC, and then in microcontrollers over the Thread protocol, Bluetooth, and also on top of Ethernet. And we are planning to test and to make and provide the support for more for Zeno to run on top of more protocols. And what happens is that what Zeno does is to create an overlay on top of this physical network, on which the Zeno transport layer can be unicast, multicast, it can be single link, but also multi-link. So if we look here at the example in this slide, so we have a physical network that is composed by IPv4, IPv6, Bluetooth, Ethernet, and this Zeno overlay is able to abstract all these heterogeneity of protocols and technologies at the physical network, and to expose in a very simple way Zeno overlay that only needs to handle or only needs to care if the transport is unicast or if the transport is multicast. Okay, so now that I showed or I provided a small flavor of Zeno and how it designs and some of the options we took, let's now try to see what happens to data in Zeno, but with a set of animations, because I think things will become more clear. So here we have an example of a Zeno network, and let's assume that this is deployed in the Louvre Museum here in Paris. So the way resources are organized in this example is we have the first segment of our data, or our key expressions that identify the data is identifying the Louvre. Then the second name segment is identifying the floor, the third the room, and then the type of sensor. We also have two storages, one that stores all the data from the first floor, meaning so the one on the top right, and then another one, which is the one on the left, that stores all the data for the second floor. And then we also have an eval function or an eval entity, which basically is able to perform remote computations. And for example, sorry, I just okay. I hope you can see it again, because
Yeah, I see it.
some macOS notification just popped out. And, okay, perfect. Sorry for that. So yes, so we have also an eval function, and these eval functions could be used, for example, to run additional analytics on top of the data, and the results of these computations can be retrieved by means of queries. Okay. Yeah. So whenever the data is produced, and what happens is that Zeno will make sure that this data gets where it needs to be delivered, depending on the subscribers and the storages that are known at the moment. So here we have a sensor that is publishing on that key expression, so /Louvre142 sensor temperature, and all the subscribers that declare their interest on such content are going to receive it. Okay, so the one on the bottom have explicitly requested for this data, while the one a bit to the right asked for all values that are all temperature values that are published, no matter the floor and the room. And on the top we have the storage that is getting all the information for the first floor. So here the lines represent the distribution path. And then suppose that we have a second sensor, so the one on the second floor that is also publishing data. Okay, so in this case, the data will flow to the other storage and not to the first one, just because they declare their interest on this data with different key expressions. And then also notice that on the bottom, we have a subscriber that is a pull subscriber. So it might be that when the data was pushed to the network, it was sleeping. Okay, this is very common if we talk about microcontrollers and low power devices. So what happens is that the Zeno router does not try to push the data to the nodes, but instead it keeps it in cache. And then when the subscriber wakes up, it will ask for the data, and the infrastructure will deliver the data, and then a garbage collector eventually will remove the data from the cache. And now let's assume that we want to know, or we have a querier that wants to know across all floors what is the temperature in room 42. And this becomes pretty simple to do in Zeno, as the querier only needs to issue a query, which will have a hit from the multiple storages. And here, note that the querier doesn't need to know the location of this data. It just asks for this information, and the network is responsible for forwarding it to all the nodes that are able to provide this information. And this is the kind of location transparency we can get from Zeno, as the network is able to forward the query to all its destinations. And then when the databases or the queryables reply with some data. The data is consolidated on its way back, and it's retrieved to the querier in a single response. So where do we see Zeno, or where we see the main applications domains for Zeno? So basically, any application or use cases that requires the distribution of data, either via publish-subscribe mechanisms, query-based mechanisms. And this includes smart farming, robotics, smart cities, transportations, energy, aerospace, and so on and so forth. We have some use cases already done in some of these application domains. I have a couple of examples to show just after. So yeah, let's move to them because they are very interesting. So here, I hope that. So here, Zeno was integrated in some cars in the autonomous challenge in order to provide some vehicular to infrastructure communications. Okay. Then here we have an example of online video game that is being developed by one of our users that basically leverages on Zeno to implement the network engine. And here we have a short demo where we have Zeno running on a microcontroller in the network and in a bridge between Zeno and DDS. And Zeno is being used to send the values the values that are published by a gyroscope, and then they are translated and sent as comments to the robot. So now some final thoughts before finishing this presentation. So some highlights that we think are worth mentioning about Zeno. So as far as we know, is the most wire, power, and memory efficient protocol in the market. We can support the whole cloud to things continuum, meaning devices that can range from cloud servers down to microcontrollers. Zeno supports both push and pull communication patterns, along with distributed queries and remote procedure calls. The resource keys can be represented as integers by the means of the resource declarations, and these allow us to have very good wire efficiency. We can support peer-to-peer and routed communications, support for zero copy. Also, we can support ordered reliable data delivery. We support fragmentation of messages and also batching of messages, sorry. And in our tests, we have, or in our analysis, we have a minimal wire overhead that can go down to 4 to 6 bytes. So finally, just to say that Zeno is completely open source. It's under the Eclipse Foundation. It is written in Rust along with all our APIs for different languages. We have a parallel implementation targeting microcontrollers that is written in C. We also have in our GitHub repository some demos. So yep, you can find this in, well, our homepage in GitHub or in Gitter, where we can have other discussions, or if you have just doubts on how to use Zeno. And this is it. Thank you very much for your attention. And if you have questions or comments, I would be happy to discuss them.
Great. Thank you very much.
Thank you, Carlos. If you have questions, there's a raise hand icon, and you can put yourself into the queue. I noticed Marie-José is already in the queue to ask a question. I'm going to put myself in the queue as well. Ken's in the queue. So Marie-José, let me, how do I enable her?
Oh, I don't want the camera. I'm already there.
Oh, okay, you're already unmuted. Great, go ahead.
Okay, I think I think this addresses a lot of pain points of people like me who are trying to do distributed applications in IoT. However, one question I have for you is that a lot of these elements, the sensors and everything, do not even have an IP address. And a lot of them are exposed through things like, industrial buses like BACnet or anything like that. And so in between Zeno and those low-level sensors, what are you doing so that the data that comes through BACnet is exposed to your interface?
Okay, so I'm not aware of that BACnet, but so Zeno can run on top of data link protocols. So it means that we don't really need IP. We can run on top of, for example, Ethernet.
But you haven't tried it with industrial buses like BACnet or things like that, because we live in a, I think in the applications that I work with, we live in what I call a Tower of Babel of different buses, different formats. Some of them are text, some of them are CSV, the data, some of them are not even CSV, some of them are just like people entering yes, no on a text file. And the BACnet is another big thing because it's actually a very, very widely used industrial bus. And so I think what you presented is extremely interesting once you have, I think, organized the lower layers, which, frankly, is the biggest job. So I think it would be interesting if you want to continue this to have the lower layer hooks that you need to get into Zeno, because if I had the lower layer links to get into Zeno, I could see how I could use it very well. And it would save me some time. And Dirk is aware that we've done work on how to establish a better way of, doing federated applications and even adding federated learning on distributed applications. So I think Zeno is very good for that. But for me, the biggest problem is how, because you say, okay, we're going to have the information from the sensor, but the information the sensor comes through means that are really, really close, that are from systems that you don't really have access to unless they write their data into a text file that you then transform into a CSV, and then that it's very bad, and you're going to park it, and you do, like there's a lot of data processing or data formatting and semantics below what you're doing. So have you guys addressed any of that?
Okay, so I don't know if it will answer your question, but so far the work we have been done around sensors is that we have a microcontroller. We can be something like 16 bytes Arduino or an ESP32, which already has some network capabilities. Okay.
So those are your systems. You haven't worked with industrial systems that are already installed.
No.
Okay, so
no.
that's exactly the crux of my point, is that if I had access to my own controllers, I would be really happy. But right now, I think a lot of the pain points and the use cases that you are presenting is that we're dealing with existing industrial systems that expose only their data through really weird means. To be that's my nice way of describing it. Weird. So I would say maybe for your next generation, it would be great. And you can contact me, and I could give you some examples on this, because I think what you're doing is very important for what I'm doing, except that I don't know how to communicate with it. So I'm taking all the time here, and I'm going to stop, but we can communicate offline.
Yep. For sure, we will contact you, because I mean, we see these. I mean, the possibility to integrate with all these industrial systems. One of the main use cases, because we need to go into the real places.
Yeah, sure.
Okay, thank you.
Thank
Ken.
you.
I wanted
wanted to ask about the security architecture. So one of the, this a lot of people see as one of the main things about NDN and CCN. So I didn't hear anything about that. So I wondered what's the sort of trust structure this is based on.
Okay, so if you need to ensure the integrity of your content, you should do it on your application. Okay, here we are not aiming as NDN was aiming. I stopped following NDN and CCN for a couple of years before joining AdLink, but we are not aiming as NDN and CCN were in providing already the integrity of the content, or to make it part of their design. So if you require those kind of features, you should make them at the user space, and then you already send the information or the signature in some other means that you are able to transmit this from your producers to your consumers.
All right, next in line is Börje.
Okay. One question on your slide where you said you have tried this on top, you implemented this on top of a lot of traditional internet protocols. Did you implement it on top of any ICN protocol like NDN or CCN?
Not really, because I mean we are targeting the same type of functionalities as NDN, CCN, and others are trying to do. So, and since we intend to have a very low wire overhead, by deploying Zeno on top of an NDN, we would already have a big overhead just with all the layers that would be under below Zeno, let's say like that.
But
also,
okay, I see. But you, in principle, I guess you don't see any problems with doing it if someone would like to do it.
No, it would be possible. I would say. I'm thinking what would be the benefit of doing it.
No, just.
But in any case, it would be possible to do. So we kind of try to abstract of what protocols are below Zeno. Okay.
So just one question. So this looks really interesting, but I was a bit puzzled because you didn't mention security at all. So is there a security framework and authentication framework?
So we have in our roadmap to have some user access control. We have some kind of, so when we are establishing a session, we have some kind of negotiation and link authentication. But let's say, so it's still things that are in the roadmap. We are not tackling them, I mean, in full mode, but they will be there, okay? So it's things that we are keeping our minds in.
Great. Thanks a lot, Carlos. So
thank you very much.
I think we should move on to give our other speakers enough time. But Carlos is also on the ICNRG mailing list, and if you check out his presentation material, you also see an appendix where he has provided additional content, also code examples and so on. So please check that out. That's really interesting. Again, thanks a lot for bringing your work to ICNRG. It seems really interesting, and I think that we could discuss this for a longer time, but maybe this is not the end. So I'm looking forward to
hopefully not.
discussing with you.
Yep. Thank you very much. Thank you for all the questions as well.
Thanks, Carlos. Okay. So next up are Red Samson and Jamie Locker, and they are winning the prize for the most inconvenient time. So they are joining from Australia. Really, thank you a lot, guys, for making this. And so they will talk about a system that they developed in their company, GT Systems.
Okay. I should say Jamie's in New York, so he's pretty cool. I'm the guy at 4 o'clock in the morning. So I think I should do share slides rather than share screen. Yeah. Is that right?
Yeah, you can share application window if you think that's what you probably want to do. That's even better. Okay, you know the system better than we do.
Yeah. Oh, except that it says I don't have a deck to share.
Well, let me see what we can do here.
That's okay. I can do the window. Dismiss that one. We'll do the whole thing. It didn't seem to know about my window.
It's probably easier.
Okay, so let me change to that. Should I turn on video? I guess maybe.
If you like, I think it would be nice.
Okay. Okay, it's not going to work.
Yeah, we'll probably take some time.
Window.
It also took some time for Carlos' presentation. So.
Yep. Okay, so that should have worked.
Okay, yeah, we can see it.
All right, now let's see what happens when I turn video on. Then it might get, I think we'll get that multiple echo thing though, won't we?
Let's see. Okay.
No, it seems to be happy. Okay, great.
Looking good.
So just so you know, where are we? Out that window there is Bondi Beach, but it's dark. So, can I change? Oh, except I can't change. Doesn't seem to want to let me change the things. Maybe I'll go back to the other one, and it might work better. Carlos, did you share screens or slides?
I think he's just shared his window.
I was sharing the full screen.
Oh, really? But it seems I can't get myself. I can't see. Well, I suppose it doesn't matter if I can't see myself, really, does it? Let's go back to that one. All right. Sorry, guys. Beginner.
Yeah. No problem.
Okay. There we go. Yes, I'm sure. Window. Oh, okay, we just share a window. Anyway. Okay, let's do that. And then I'll just okay, so you should have my first slide up now.
Mm-hmm.
Okay, so I can't see myself, but I'm sure that'll be fine. Okay, so let me just start my clock.
So I think if you want, you have to click on presentation view. Then you, I think, see everything again. So in this top right line of buttons.
Okay.
Yeah. Does it work? All right.
Oh, it's a PDF, right? So maybe you can just go view full screen.
Yep, I can do that. See what happens then.
That's perfect.
I still can't change the page, so that's all right. I'll go to the presentation and assume that I look half decent for you guys. I think. Okay. All right. So we've done, Carlos, some of the things you said were very similar to the things that we say, I think with one fundamental difference, which is that you're working at a transport layer over different network layers. And we came to this from a slightly different perspectives. So let me just leap into that, and it'll become. This became our mission. It wasn't our mission beginning. So this is a timeline which you can, to put it into perspective. But I think the most useful slide is this one. Because what we really set out to do back in the early days was to really to fix adaptive bitrate buffering and the spinning wheel of death, which we thought was a pretty ordinary thing. And in doing that, we took a fairly fundamental view of things and came up with a what turned out to be a fundamentally different concept. Very simple, but very different from the way the internet ran at the time. Which was a lot more crazy back then than it is now, trust me. So we sort of borrowed from some work that we did with CSIRO and Peer Assist, where they had done something very similar to a BitTorrent patent application, where they combined peer-to-peer with super servers, for want of a better word. And they got some very encouraging results. And particularly, the very important thing to bear in mind is that we've always been application driven in this. We were driven by video, because we were in the manufacture on demand of CDs before this. We then had a customer who wanted to do video, or wanted to do movies online, and so we were driven by basically building a better streaming system. And this was before Netflix existed, by the way. Or sorry, Netflix was still mailing DVDs when we started this. And so we did what everyone did. We stood on the shoulders of giants and BitTorrent and GitHub, et cetera, and sort of thought about it and said, well, okay, what if we do this properly and start again? And we came up with a very simple concept, which we called, secure peer assist. And it was just this simple thing of ingesting, and it was based around, as I said, peer-to-peer and OTT distribution systems. This simple idea of, there's an ingest process. You have to process the content. You slice it up, you tag it with, as we said at the time, either a hash or some other efficient database mechanism, leaving the door open for things that we would learn about, like name domain networking, content-centric networking sometime later. But then one of the fundamental ideas we had was to route on those tagged slices or packets, and then to do that intelligently with optimization. And as I said to someone the other day, the I in AI for networks isn't that I. You don't have to be that smart to make massive improvements on this. And then we came up the same idea as originally CSIRO and BitTorrent, etc., which was peer-to-peer with super pops. But we left the door open for everything to be a peer, and for it to be a mesh network, and a distributed storage network and a distributed computing network. So that's kind of was the starting point back in. We started the R&D. We did the work with CSIRO in early 2000s, and then we did MOD for a while, and then we did and then we did the work with the customer and came up with this. But we then discovered a thing called IPFS and Protocol Labs. Interplanetary file system, what a great name, and of course that was an implementation of our idea, which was the file system I'd been running around looking for and saying, we need this. But it really was. It was a great idea when we found it, but as time went on, it became clear to us that there were some problems associated with that, which was that it didn't scale for distribution. It was great for storage, but didn't scale for distribution. And in particular, we became aware of that when they published some RFPs early last year, I think, for some R&D work to help them scale. And that's when we formed the team. We were working with Nokia by then at this stage, and Nick Locker and our man at Nokia introduced us to Hammy, who's here. I don't know whether you want to say hi, Hammy, if you got your mic unmuted.
Yeah, hello. I was at Bell Labs for a long time and joined them when they were working on this problem.
Yeah, and so we formed this project team with a bunch of other really smart guys, and sort of merged all the work together to respond to Protocol Labs' sort of call for help. But given that we both really liked their distributed storage system, and really a lot of it was merging the work that Hammy had done in modeling and optimization at Bell Labs with the work that we'd done, around content distribution and peer-to-peer and sort of our version of that. And in the end, we kind of came up with a solution. We first of all, we had to learn how it all worked, and then we discovered the limitations. And there were some very strong points to, as Hammy says, to the storage side of IPFS, but it had some limitations in distribution, which we'd addressed from the beginning in distributing video. And then there was a paper, and I was trying to remember whilst I was listening who wrote the paper, but I think it was someone in either CCN or ICN or NDN had written a paper that said it might be really interesting to smash together IPFS with name domain networking or content-centric networking. I think they said content-centric networking. And we're like, what's this content-centric networking thing? I'm ashamed to say, and we then, we dived into that whole thing and we went, wow, this is nirvana. This is a fully, particularly NDN, which is where we ended up. This is a full implementation of kind of our idea. But then, what if we put those things together? And then I think we were on a call, Hammy, one day, and you said something and I said something, and we said, well, what if we smash together that deterministic hash Merkle tree system of IPFS with the less deterministic system of name domain networking? What would that need? And we kind of worked out that what you had to do is to have a unified namespace, and that we think that's one of the most interesting areas that we could potentially all work together on, is really defining and standardizing that namespace, that unified namespace, because that then kind of draws everything together. And as I've said in the white paper, which is up on the website, I'll give you the URL for it later, that we could actually unify kind of everything. And so we ended up with a thing we called this hybrid adaptive routing system, which does both name resolution and name-based routing. And when I say routing, it's an NDN concept of routing. So we're essentially a layer 2 protocol, but with the NDN bits to stop to do stop feedback and load balancing, etc., or loops, I should say. But combining all of the the best bits of a layer 2 protocol, and so the fundamental thing, which I should probably go down to, which you guys, I'm going to have to go too far. Never mind. But you've all seen the narrow waist picture, and so basically we were saying, okay, we're gonna switch/route at the network level with these tagged packets or frames or whatever you want to call them, and that was the fundamental difference. Is that we kind of said, well, we didn't even consciously say IP has reached its limits, but that was kind of the outcome of what we were doing. And so you add all this then you get all these other benefits of, location-based and multicast, and it's fully distributed. And then we combine Hamy's work around elasticity and virtualization. And then we came up, and I remember when, Hamy, I don't know if you remember when we first spoke, the very first time ever, you asked me one question. You said, do you have a global optimizing system as well as a local optimizing system? And I said, yes. And you said, good, that's the only thing that works. And I guess when we make our claims here saying, this stuff works and it's very efficient, Hamy's the guy who's kind of proved that for us. He's been modeling this stuff for a very long time, and we might get him to talk about that in a second. So in fact, we might do that very soon. But in essence, and this only kind of dawned on us over time, is that what was happening is that the network is becoming the cloud. When you take this fundamentally different approach and sort of smash the two things together, then the network becomes the cloud and therefore the computer. So we're talking really about distributed cloud and distributed computing. So this is what we do. I won't go into too much detail about that, except it turns out, having used Hamy's very sophisticated models, that doing it this way is incredibly cheaper and incredibly more efficient. And when I say incredibly, I mean, up to 50%, but we'll get to those numbers in a second. And you push things out to the edge, and of course you improve latency significantly as well, and you save your backhaul costs, et cetera, et cetera. So it's very secure. I mean, we were working with Hollywood. We don't even say BitTorrent in the presence of Hollywood. We call it the other protocol. And so we were secure from day one, and it's just got more secure with the things that have come along since. So fundamentally, that high value content is encrypted at ingest, and that's what makes it secure, using Hollywood approved algorithms, DRM, etc. But also that the name domain networking and content-based networking adds another level of security, particularly around signing of packets. And we always had this idea and concept of sovereign identity, and then during the IPFS period, in that time scale, we met a guy called Jonathan Holt, who's one of our advisors as well. And John's very involved in IPFS at the development level, but also as an investor in Filecoin, and a very smart security guy. And he has come up with a sovereign identity system based in the WC3 distributed identity architecture, for want of a better word, that really addresses security and login from the edge rather than centralized. So this is how we work. We model, design, build, handover, operate. We work as we sort of describe ourselves as a 21st century Bolt, Beranek and Newman, BBN. I know that sounds a little bit ambitious, but that's a simple description of kind of who we are. And we're very, very keen to find ways of working with everybody. And although we've applied for patents, that's about trying to redress that balance between people who built the internet for free and the people who make a lot of money out of the internet today, and trying to find a space somewhere in the middle where people get rewarded for their work, but the internet gets sort of built and taken care of. So we're very, very keen to explore those models more. So I think I'm probably going to hand over to Amy at this stage and let him just run through the stages of, this is our very simplified view of how you would implement this, but we also talk about the very different bits. Amy, do you want to run through these?
I can talk to these, but you have to move
I'll move the slides. Yeah.
Yeah. So yeah, I mean, just to one of the first concepts that we try to exploit is the idea of is not just the content lives in the network, but the applications live in the network, right? So now we have all these available resources that we want to utilize. Everything is getting distributed, and we have compute storage in the network, and we need to understand first what's the optimal use of available resources at core, edge, and peer levels. So the first work we did is just modeling different applications running over this network and seeing really if it makes sense where those functions end up being running, what is the optimal place where they run, what is the optimal place where data gets stored. So when we start modeling these networks, we see that if we end up allowing, unlimited, if we unconstrain the use of storage and compute resources at different layers, where do these applications and data end up moving, and how much cost reduction we can get. So the first stage was just looking at that and saying that, as we move towards more low latency applications, and even for just content distribution, of course, we get a lot of bandwidth cost reductions as we start moving both data and functions to the edge. So, and just for on-demand video streaming and live video streaming, we end up getting numbers on around 40% for network cost reduction that we think can go even greater when we really go for industrial automation and augmented experience services, where you really have that low latency requirement. So that's the first stage. Even without going into changes in the networking protocols, what can you get by just putting functionality and data at the right place, right, from a placement perspective? You can go to the next stage. Then the other idea, of course, is to exploit programmability and virtualization. So as you use virtual machines and you can program the network in between, you get additional cost reductions, essentially from over provisioning. So you reduce over provisioning because you're using you have a network that is more elastic. Now, data and functions live in the network, but they consume virtual resources, so you can scale up and down the use of resources whenever you need them. So you get an extra 20% in the simulations that we run when you add that elasticity to the optimization. And then finally, we have a stage where we say, okay, if applications and data really live in the network, the first thing you want to do is to optimize the use of resources. The second thing is to make sure that that use is elastic and is dynamic. The next thing is change and use more efficient networking protocols. So the idea of the final stage is using these integration of name resolution routing and name-based routing. So using name resolution routing for distributed storage, for persistent available distributed storage, and using name-based routing for fast access and delivery. And we think that integrating both systems is really the best way to use the benefits of both worlds, right? I mean, they do have limitations on their own. With name resolution routing, it's an overlay solution. You have is a slow system for resolution, but it's really great for persistent distributed storage. And name-based routing is great for efficient delivery, but it has also some limitations in the amount of forwarding state that you can keep. So putting them together, we think it's a great solution. So adding that functionality, and then the last aspect is adding an element of AI. Still on that same slide.
Nope.
Which is just, in this case, is a modeling exercise, but we think that when things get so complicated, when data really lives in the network and you have so many options to access data and to run functions and computations, an element of AI that combines global optimization with local AI agents can help just optimizing both the resource allocation and the routing and caching decisions in a better way. And then, maybe Red, maybe you
then
can
you join it all up. Yeah. So then once you get to that level, then you say, okay, well, if we do that, how does that have to work? And we very quickly got to the point, another colleague of ours, Matt Moran, who's a very, very experienced at OTT and networking stuff. And he said, no one's going to trust us, because if you have an optimizing AI, then someone has to run it, and of course that's not going to work. We quickly realized, but then when we said, well, I kind of said, well, why don't we just let everyone run their own and make them all talk to each other? And typically of me, it turns out that not too many people are doing that. So we think that, again, this is an area which we think is very fertile for cooperation, where you have this concept of distributed local agents which are optimized and perhaps even trained in locally, which is a kind of different idea, for a local optimization and autonomous behavior, and maybe hopefully some emergent behavior, and then you feed up information about the network up to an optimizing intelligence. But there isn't just one, there's multiples of these, and then you have to join them up at a couple of levels, which we'll have some slides on in a minute, in order to really to have an AI API, I guess, for want of a better word, where you're sending stateful information in between subnetworks, and it joins up into a universal content distribution network, which is this concept that we have. The good news is we found someone who kind of likes this idea and actually wants to build it, which has sort of stunned us a little bit. But as I keep saying to the guys, it's really just about finding someone who wants what you've got. And so there's a bunch of guys putting some satellites up in medium Earth orbit as a backbone, and they want to do this. First of all, they're greenfields, which is fantastic, and secondly, they want to do it properly, literally their words, and thirdly, they've come to an understanding which seems to be growing at various places around the world, and I'm sure there's plenty of people listening who may have come to the same conclusion, that IP and may have sort of be getting towards the end of its useful life, and maybe it might be time to thinking about re-architecting stuff. So these guys were open to that possibility, and when we came along, as they said, we're the big fat pipes, and you're the guys who fill the pipes, and we kind of realized we needed to do that, but we didn't quite know how, and so it's turning out to be sort of a bit of a marriage made in heaven, and it could get quite interesting in the next very short space of time. So that's a system block diagram of merging the two things together, which talks a bit more about that. We won't go into too much detail about the rollout. It's global. We're doing Africa first. We'll hopefully do Australia very soon. We're working with these guys. So this is the really interesting thing. You know, these are the people who are building existing networks, or maybe building future networks in the case of NVIDIA. And so I think, you know, that's the system block diagram out of the patent, which is similar but different to some of the earlier ones, which are more involved. This is the one I wanted to get to. You know, you say, okay, well, how are we going to do this? And it ends up being reasonably simple. It says, you know, that you just basically put, well, this wasn't so simple 10 years ago when we started doing this, or for 15 years ago, but now you've got open routers, you've got guys like Arista, and believe it or not, Nokia have now an open SI Linux based service router offering, which is what we're going to do this on initially, and then with some of the NVIDIA AI stuff at the edge. And you can, in fact, put a custom protocol as a stack alongside a classic TCP/IP stack, and connect them both to the switching and routing bus, and then you know, if it's a span enabled packet, then the span stack deals with it, and if it's a TCP/IP packet, then the TCP/IP stack deals with it. And obviously there's some things you have to do about tunneling, etc., but that's all beautifully dealt with in NDN already. So then you say, no presentation would be complete without a slide on the metaverse. But once you have that fundamentally different architecture where the network is the cloud and the distributed computer, then you say, okay, well, how do we make this work in terms of, you know, joining up all these? So we video kind of tick, we've done that, and got some amazing results for that. And then, you know, now we need to look at the virtual worlds and graphics and computer-aided design, etc. And you know, the guys who deal with it the most, of course, are in NVIDIA, or one of, and they've come up with the same concept and said, well, we need a set of standards, which Pixar have developed for universal scene description, and then we need a set of tools and some brokers, for want of a better word, which they've come up with Omniverse and Nucleus. You know, but at the moment they're focusing that on corporates and, you know, guys like BMW, you know, so that they can have the CAD systems that design the cars talk to the CAD systems that design the factories. But we've talked to them and said, have you thought about pushing that out into the network? And they said, well, no, but that seems like a pretty good idea. So we're having those discussions. And of course, you know, the essence of the metaverse is perfectly suited to this, to kind of our view of the world. There's a fundamental thing in all of this, which Carlos got to, you know, which is that the network now is the cloud and the computer, and it therefore needs a set of instructions, the two most fundamental of which are publish and subscribe. And so then a publisher would simply publish their content to the network, and the network takes care of the rest. And then you as a consumer would say, I want to subscribe, and the network takes care of the rest as well. This thing needs to be standardized, obviously, you know, that's a huge thing. And these, as we say, are the areas that there's a nice set of rules from Tony Parisi, which, you know, there's one metaverse, it's open, it's in brackets are our additions, it's enabled by a network, that network is the internet. And this is how these things roll out. Some thoughts for the future, you know, is as I talked about, we perhaps need some new funding and operational models that sort of combine the best of everything. Clearly, quantum computers are a huge thing, transport, but I don't know much about this, but it seems that lasers might be kind of good for that. They're certainly good for quantum key distribution, which the network we're working with does. And then, of course, distributed artificial intelligence, where you're doing local training, perhaps, and machine learning, the concepts of play to earn, to train, you know, like you would train a Tamagotchi, you'll train an AI agent, and then, of course, the golden fleece of general artificial intelligence. So these are the guys who we're kind of working with, and this is our claim, and this is my favorite saying at the moment. one day you go to sleep and you're the czar of the whole of Russia, and you wake up in the morning and you're not. So thank you very much for the opportunity to talk. And sorry, I think we've gone a fraction over time, but I'll kind of open it up to questions.
No worries. Thanks a lot, Red and Remy. So this is really quite intriguing. So you, I think, raised many interesting aspects. There's also some thoughts that have been discussed in this community and also the computing in the network community a lot. Yeah, so we don't have that much time. So I think what I would like to do is just ask people who have questions to reach out to you, if that's okay.
Yep, love to.
Because I think there would be many like quite detailed technical questions next,
Yes.
but I think it probably takes a long time to answer those.
It does. It takes a long time to get your head around this. We've had 10 years and you've had 20 minutes. So, you know, and as I say, the white paper is up on the website. So gtsystems.io. And then if you add just /white paper, you'll get the white paper. And then there'll be an open link to it in the next day or so.
Yeah, that's great. So again, I think many of us have thought about like the connection of IPFS and NDN, for example, and so on. So I think you would get some interesting questions, and so hopefully we can have you again in the future and then talk about these things in more technical depth.
And look, we'd love to become involved in the dialogue. I don't know what's required to do that, but more than happy to get involved in, you know, discussion channels and answer questions, etc. Great.
Yeah, thanks a lot. Super interesting, and especially thanks for making the time, Brett.
That's okay. You owe me a beer.
Yeah, yep, I know. you get it. Next time we can all travel again.
Yeah, exactly.
is in Australia, so I understand the time differences between the East Coast, Europe, and Australia. So it's quite challenging.
It's great if we're organizing meetings because we're kind of in the middle, and then we make everybody at the edge suffer a little bit rather than us suffering a lot. So
well, I think we found that the best thing was actually maybe doing it from the West Coast of the US, which is bad for everyone.
Okay.
Thank you so much.
Thank you.
Thank you very much. We really appreciate the opportunity.
Thanks. Next is Junshao Shi with this presentation about Nts Api Design. And
yes, I'm waiting for the user to stop sharing.
Yes, and we have to approve the, yep, here you go.
Hi, my name is Junshao Shi. I am a guest researcher at NIST, but NDNTS, this is my personal project, so this will reflect personal opinions. Today, I'm talking about NDNTS API design. NDNTS is a set of NDN libraries for the modern web. It is modern JavaScript libraries. It can be used in both TypeScript and JavaScript projects. It works in Node.js and browsers, has more than 90% of test coverage with automated and manual browser testing on desktop, Android, iOS. It works standalone without a forwarder, or it can connect to forwarders such as NFD and NDN DPDK. The project is so far actively maintained. New features are added regularly, and it supports the latest NDN specification. This talk is about my personal thoughts on NDN low-level API design. By low-level, I mean things like packet decoding, fragmentation, phase, and retransmission logic. There are other API are not low-level, such as data-centric and toolkit and a common name library. I will not focus on those. I will also talk about the unique challenge in building an NDN library for the web, because due to the specialty of the web is code size is a primary concern, and the browser is like an operating system, but it differs from a traditional operating system. So let's first get into the low-level API. Many people would say low-level API is boring, and this is probably true because the NDN team official position is we encourage application developers to use high-level APIs such as data-centric toolkit and common name library, because those high-level API can abstract NDN complexity away from the application developers. However, my belief is interacting with low-level API is unavoidable, because if you try to build a high-level API, the library developer would have to deal with low-level API. And also, high-level API are unlikely to cover all possible application needs. So sometimes applications still need to interact with low-level API. Therefore, I believe it's still important to design a good low-level API. NDNTS has some unique opportunities because first, NDNTS is not the first library. I am rarely the first to implement a particular feature. Instead, my preference is to write some applications with existing libraries and look at how other developers are using the library to make applications. Through those, I can feel the pain points of existing library, especially which API are cumbersome to use and which code snippet have been copy-pasted in multiple places in the application because it's missing in the library. And then I can improve those areas in NDNTS. The other opportunity is that NDNTS is a personal project, so I can have the freedom. I don't need to promise backwards compatibility. I can take my time to refactor the code without worrying about deadlines. And I can invite people to watch my push-up videos that are delivered over the NDN testbed, then collect video playback metrics to improve my congestion control implementation. But back to the APIs, the first one I mentioned is TLV decoding, but it's with TLV evolvability considerations. I will do an example. The example is the NDN link state routing daemon, NRSS LSA info structure. The structure looks like this. It has a TLV type number, a TLV length. It contains a name, a sequence number, and an expiration time field. Those three are sub-TLV elements. But it looks simple. Then we look at the NDN specifications. There is a section called Considerations for Evolvability of TLV-based encoding. That section dictates that if the decoder encounters unrecognized or out-of-order sub-TLV element, there is a specific behavior to follow based on the TLV type number. If the TLV type number is less than 32 or is an odd number, the decoder must abort decoding and report error. If the TLV type number is an even number, then the decoder should ignore that TLV element and continue decoding. But with this behavior, it means you can have some unrecognized fields inside the LSA info between any sub-TLV elements, and the decoder should be able to handle that. And that makes decoding somewhat more complicated. So how to write the decoder in the libraries? NDNTS adopts a semi-declarative structure. So the code looks like this. I have a thing called the EV decoder or evolvability aware TLV decoder. To use that decoder, you can declare each sub-TLV using this add function I can add with the TLV type and a small lambda function of how to handle the TLV value or how to handle that sub-TLV. The lambda function can include extra logic such as saving signed portion boundary, which is useful when I decode the data packets or decode a certificate. But it's not here, and here it's very simple. And then it's an evolvability consideration I mentioned earlier. It's handled automatically by the EV decoder. With NDN-CXX, the code is a lot longer because NDN-CXX doesn't have such decorative thing. Everything is a procedure. So, and it's a decoder function I'm showing here. It doesn't even support TLV evolvability. It can be added, but then it will make the code even more complicated. Python NDN so far is the shortest because it's using a reflection-based decoder that is purely declarative. But Python NDN's decoding function, it is less flexible because earlier I said that there could be extra logic such as signed portion boundary, and Python NDN cannot do that easily. You have to add extra code. And also Python NDN's decoder forces the class structure to follow the TLV structure, and it means application have to be exposed to encoding details. Sometimes you don't want that. But this kind of reflection-based decoding, it's not really possible in JavaScript, but I can do something similar, and that's something I want to explore in the future. Then the other API is the face that is common in many other libraries, but in NDNTS, I named it endpoint. So traditionally, face is a central concept of many NDN client libraries. It's in NDN CXX and NDN CCL. Python NDN has it slightly different. But what does face do? Face does two things. One is perform interest data matching. The other is through the management doing the prefix announcement. Each face is normally corresponded to a single transport. But the face only do these two, and then if you have a socket error in the transport, application has to handle it manually. Or if you want to reach interest retransmission, data signing, data verification, data buffering with in-memory storage, everything is manual. NDNTS evolved the face into a new concept called endpoint, which is more powerful. In the endpoint, the consumer can, on the consumer side, the library can provide automatic interest retransmission and automatic data verification. For the producer, I can do prefix announcement, data buffering, and the data signing. You will see some examples later. And each endpoint can have more than one transport uplinks that can connect to other NDNTS applications, to forwarders, to IoT gadgets. And any transport error will be handled automatically if possible. Having those all in the library, this allows the application to focus on the application logic. So 3 examples. First is the consumer's interest retransmission. In NDNTS, if you want an interest retransmission, you just need to set one option. So this is how you write a consumer. You prepare the interest and call the consumer function. The data will come back later if possible. Then retransmission can be enabled. Say I want up to 2 retransmissions, and the rest will be done by the library. If after retransmission data still doesn't come back, there will be errors, and error handling is still necessary. But compared to other libraries, then developer has to implement the interest retransmission. Basically, it's this flowchart they have to implement manually. And as I observe in the implementations, most developers get it wrong in some places. On the producer side, NDNTS can support automatic data buffering. The use case for automatic data buffering is when the producer want to prepare a multi-segment response to one interest and then wait, and the subsequent segment will be answering the later interest. A concrete example is in the NFD's management protocol dataset publisher. When you can send the interest to NFD, ask it to return all the RIB entries, but the RIB can be larger than a single segment. There can be multiple segments, and there is a buffering needed. In NDNTS, it's automatic. Your producer callback function or lambda function can prepare all the segment and insert it to a data buffer. Then when the subsequent interest arrives, it will be satisfied from the buffer automatically. Your producer function will not be called again. In other libraries, the developer has to manually query an in-memory storage for every incoming interest, which would be more complicated than this. And NDNTS can automatically perform data signing and verification. All you need to do is provide the signer and the verifier to the endpoint constructor. And then your lambda function or your consumer does not need to do that anymore because the library will handle it for you. NDNTS support both signer and the verifier. They can be either a fixed key or a trust schema that choose a key based on the data packet name. For other libraries, the developer has to call keychain and validator manually. And all those are small things, but they lead a lot of code repetition. And with NDNTS, you can eliminate repeated code. And as I mentioned earlier, one of the challenges in NDNTS is that the code size is a primary concern on the web because every kilobyte of code must be downloaded over the network. Visitors will expect your web page to load within 5 seconds. That metric is called time to interactive. And to download within 5 seconds, what you can download, the code size budget is 170 kilobytes compressed. So to solve this problem in NDNTS, what I can do is I try to reduce the core features that are always included in the compiled code. That if an application needs extra features, they need to import the module and pay the overhead. For example, data buffer feature I mentioned earlier, its implementation so far is quite complicated and has a lot of code. Therefore, by default, it's not there. But if you want it, you have to import those data buffers, that module, write this code. It's a little bit of boilerplate that is not really desirable, but it's a trade-off between API simplicity and web page performance. And NDNTS support a lot of transport that is under that endpoint layer. So this is a simple comparison chart. Notably, I recently added HTTP3, which runs over quick, and through a proxy or a Python-based proxy program, NFD can also support HTTP3 transport. This allows me to do video streaming more efficiently than using WebSocket. Since WebSocket has a TCP over TCP problem, but HTTP3 runs over quick, which is over UDP. Then you don't have double congestion control. And the next thing I want to explore is the WebRTC transport, which could allow two browsers running NDNTS to talk to each other, but I don't have that one yet. The next API area is the security area, especially the keychain and the crypto. NDNTS keychain is implemented with the Web Crypto API and the IndexedDB when it runs in the browser. So Node.js is different, but in browser it's those two. And this is how I use the keychain. It's some code. So first I can open the keychain. Effectively, it will open an IndexedDB that stores the keys and the certificates. In the browser, IndexedDB is able to store Web Crypto private key without exposing the key bits. You will see it later. Then I can call generate a signing key, and it will generate non-extractable keys using the Web Crypto API and store it into IndexedDB. The private key bits are not available to JavaScript code. This provides some sort of isolation or protection against someone stealing the keys. Then NDNTS has a client for the NDN certificate management protocol. So I can call request certificate. It will communicate with a remote certificate authority and obtain a certificate. After it succeeds, I can finally save that certificate into the keychain. But there are a few limitations with Web Crypto. First, Web Crypto requires a secure context. Effectively, the web page must be delivered over HTTPS to use Web Crypto. This is a requirement by the Web Crypto specification. But not every page is over HTTPS because someone from Philippines, they wrote to me, in their country, they don't have a lot of internet, and locals are communicating over the coffee shop hotspots. In that case, they don't have internet, they don't have DNS, they have no way to get a certificate from Let's Encrypt and similar things. So NDNTS security feature will not work in this environment. I have not found a solution to this. The other is Web Crypto has limited algorithms, the crypto algorithm. Some newer NDN specifications want certain crypto algorithms that are not in Web Crypto, so it means I cannot really implement them. Yeah, one of them is Flick. Flick says Flick gave one option that is AES CCM. Web Crypto doesn't have it. Of course, I can. If I design the application, I can pick the other, which is AES GCM that is there. But if an existing application chose to use AES CCM with Flick, then NDNTS will not be able to interoperate with that application. There are some alternatives to Web Crypto. First is JavaScript crypto library, such as ASM Crypto. The other option is I can compile Rust Crypto as a WebAssembly module. But both has drawbacks. First is the code size increase by at least 10 kilobytes, maybe 200 kilobytes in the case of certain ASM Crypto. And the keys are not protected anymore. Remember, in Web Crypto, the keys are non-extractable, but if I use JavaScript Crypto, it's not there anymore. Then there is also no effective way to cleanse memory. And if the code is delivered over plain HTTP, it's even worse. First is man-in-the-middle attack, since it's not encrypted HTTPS anymore. And also there is no secure random number generator. It basically means I cannot generate private key safely. So far, NDNTS is still limited to web crypto only. I'm not sure whether I want to relax that, but currently no. The last issue is not really API, but it's closely related, which is how do you name a browser? Because name is a secret source of NDN, as Alex said. For the anonymous users, it's somewhat simple. So this is the code I showed earlier. When I generate a signing key, I need to give it a name. So my current web applications, they only serve anonymous users. I don't authenticate them, so I can just use random names. When the user comes in for the first visit, the page generates a random identity name, then requests a certificate, store it in the keychain. When the same browser opens the page again, it will reuse the existing certificate, the same name. And if that certificate has expired, or if the keychain is deleted because the browser cleaned it up, then I just go back to the first step, give it a new name. But this only works for anonymous users. If I want any user authentication, then it's a different challenge. User experience is important. So what user most familiar with is either username plus password, or email me a magic link. And internally, it can be implemented as obtaining a short-lived certificate from a certificate authority that is controlled by the web server. Then we can also try to port OpenID, OAuth, WebAuthn, those specs, but do it over NDN. It will interact with an NDN authenticator app that the user could download or self-host on their own server. And inside it, that app should contain a certificate authority that are controlled by the user. But in either case, we should have a streamlined user experience, because visitors do not care whether the web page is using NDN, they just care about a good experience. So finally, this is some resources that can help you start coding with NDNTS if you want to. I also want to highlight NDN Play, which is a web simulator for NDN. It's built with NDNTS by one of our collaborators, and it's right nice. So check it out. Thank you.
Great. Thank you very much, Junxiao. I could imagine there are some questions. Maybe let me. Okay, so yeah, Dave, go ahead. Maybe your audio doesn't work.
What?
So, Dave, we can't hear you. Probably the same issue as before. Yeah, maybe in the meantime, one question, Junxiao. So in your API, how would you deal with situations when things go wrong? So, for example, when the transport protocol has a failure, do you have some kind of exception system?
If transport fails, the transport will get reconnected automatically. Then there is, in most cases, there will be event emitters. You can hook into the transporter to find out it's up or down. But every transport will try to reconnect indefinitely, following exponential backoff.
Oh, okay.
There are some transporter you cannot. The web Bluetooth you cannot if your gadget is offline. The browser don't allow you to reconnect. But WebSocket, web transport, they will all reconnect.
Okay, got it. Thanks. Are there other questions? I think Dave really still has issues with his audio. So what would you say is, say, the attractive scenario for using NDN TS? Is it like an experimentation environment for web applications? So what was your intention in developing this?
Oh, I don't really understand the question.
So so it looks like, I mean, one of the interesting features here is that this can run in a browser. So
Yes.
are you trying to experiment with like building web applications on top of this, or what is your main motivation here?
I have the only library that can run on the browser. The previous one is called NDNGS, but it's no longer being maintained.
Yeah, okay. Okay. Wait, there's something going on in the chat. Okay. All right. Yeah, so personally, I think this is a really nice idea, and yeah, we have started using NDNTS for some experiments, and so I think one of the interesting like possible next work topics in ICN could be exactly how would you really build web applications, and you also pointed to how would you name the browser and provide something like an endpoint or something, a reachable name to the web application. And I think these are really interesting questions, and I think it's really ongoing work and needs further thoughts. So thanks again for introducing this to us. And yeah, okay, if there are no further questions.
Someday I will start implementing Flickr, but when it has like encoding specifications.
Yeah, okay, I mean, we can quickly discuss this. I mean, there are implementations of the spec in Python, for example. You probably have seen that, right?
I know. It's
Okay.
for CCM, but it's not really specified in ABNF syntax.
Yeah, that's correct. Okay. Just a moment. Okay, yeah, thanks again, everybody, for presenting your work and for attending the meeting. I think it was quite interesting. And I think many presentations today will probably lead to further discussions. Let's do that on the main list or reach out to the individuals. Here just some thoughts by Dave and myself about next meetings. So personally, we think it's a good model to kind of have this interim meetings. So kind of avoiding these online IETF meetings, because these weeks are typically really busy for everybody, and also we have less control over the time slot. So our thoughts were like, so if next IETF in March is actually happening in person, we would try to meet there. If not, we would go for another online meeting before or after the IETF week, so similar to this one. Yeah, quickly, please note that ACM ICN next year is taking place in Osaka, Japan. So let's really keep our fingers crossed that travel will be possible then. So you can expect the call for papers and other infos fairly soon. And with that, yeah, thanks again for attending. Wish you a really nice holiday season, and let's be in touch. Looking forward to further discussions with you. Thank you.
Thanks,
and goodbye.
everybody.
Bye.
Thank you. Have a nice weekend.
Thanks, you too. Goodbye. And special thanks to Ken for taking notes. It was super useful.
Is there a web page for ICN 2022 yet?
Not yet.
Okay.
Hopefully soon. Okay.
Actually,
bye-bye.
I think there is a web page, isn't there? I'm not sure though.
Last
I
time
thought I
checked, there
remember
was-
seeing a link, a URL, but I don't remember what it is off the top of my head. Sorry.
Maybe you can send it to the list if there is one.
Yeah, I'll look, and if there is, I'll send it to the list. If you don't see anything, it means it's not there yet.
Happy holidays, everybody. See you.
Happy holidays. Goodbye.
Bye. Interrupted relief.